Welcome back, chemistry fans. This is your day 35. This is topic number 7. Unit 7, topic 5, part B. This is where I am going to try and add on a new topic to what has already been explained to you about hybridization. So, in this idea of hybridization, what we had discussed previously is the concept that all of these bonds sometimes are overlapping, and we can't explain that truly with the model of the Lewis structure. And so we had to develop some reasons why it wasn't working. And so that's what I'm going to work with you real quick with. So you're going to see these weird orbital diagrams that I need to go over you with. They look like these little, I guess these are hexagons, 1, 2, 3. Yeah, these are hexagon shapes. Now, off to the sides of them, however, you will notice that there are these dashed lines, and those are somewhat similar to what we already know. And so if we had an element such as, let's just say nitrogen. Nitrogen, we should know that as a Brinkelhoff, it is triatomic. I'm sorry, it's not triatomic, it's diatomic, but it has 3 bonds on it. Well, we've just taken that for granted. That's the want minus have. But why isn't it 4 bonds? Why is carbon not diatomic that has 4 bonds? So when I do the want minus have, I would have 16 for the 2 nitrogens, and the halves I would subtract, and that would give me 6 divided by 2 gives me 3. Well, if I do carbon, the same want minus have, I would have 16 minus the carbon is 6, so that would be 12. 4 divided by 2. Well, it should be diatomic also, if the math works out here, but it doesn't. So this is where we're going to try and show you how to do antibonding versus bonding. So when you see these hexagons, what you are filling in are the number of valence electrons. And I'm going to put a second one over here on the side, and this is going to be the one for the 1s2. And so with the 1s2, we would have the sigma bonds because they're only single bonds for the 1s, and then we would have the sigma star 1s. Now, what the regular sigma means is it is a bonding electron. But if I have anti-bonding, 2 electrons are going to push against one another. 2 of them want to bond, 2 of them don't. They cancel each other out. So for nitrogen, it's element number 7. So we're going to fill in this orbital diagram, but it shows bonding and anti-bonding. So I will put in the 1, 2, 3, 4, because this is for 1 nitrogen on the left, this is for 1 nitrogen on the right. Now, once we've done that, we're going to take those 4 electrons and we're going to place them into the sigma and the sigma star location. 1, 2 down at the bottom. You always start lowest to highest energy, and then 1, 2 up here. Now, notice what happens. Those 2 electrons are canceled out with the 2 on the top. The sigma and the sigma star, the bonding and the anti-bonding canceled each other out. And so that's why there's no bonding on the first energy level for nitrogen. And we do the same thing now for the sigma 2s's. I have 4 electrons there. So right now, these are both, again, this is for this nitrogen, this is for this nitrogen. That's the same nitrogen on the left and on the right. So these are my 4 electrons, and we've got to get ourselves up to 7. So I can put those in right here already for the nitrogens. Now let's fill in this orbital diagram, 1, 2, and then 1, 2 electrons. Notice again, electrons number 3 and 4, they are canceled out because there are 2 bonding electrons and 2 anti-bonding electrons. So that's reason why there are no sigma bonds that are causing the double bonds. It looks like all of the triple bonds are going to happen from the pi's. So we have a total of 3 and 3, that's 6. So what we're going to do is we're going to put in 1, 2, 3, 4, 5, 6. Notice there are no sigma star. There are no antibonding. So what that tells you is that these three electrons are going to, I'm sorry, these three pairs are going to create the triple bond that's in nitrogen. Okay, let's try another one real quick. So let me scroll down here. And let's take a look at hydrogen. And then we can come back up and do another one. Now, in this scenario, the hydrogen, each one of them has a single bond, and we know that again, we can do that. All hydrogens, all halogens have single bonds, and we'll prove that to you in just a second, again, with this new method. Hydrogens each are element number 1, so here's 1 and here's 1. They have a total of 2, and these 2 make the single bond that we show in the Lewis structure. There are no antibonding, so that's the reason why this hydrogen can occur. Now, the bond order, if we want to calculate this, remember we have a bond order previously that we've calculated. The bond order was always the number of bonds divided by the number of locations. And so we have one bond divided by one ligand, and that was 1 as our bond order. Well, this is another way whenever we have antibonding that we can calculate the bond order. So the number of bonding electrons is 2, the number of bonding antibonding is 0, divide by 2, and we get the same value. So it's 2 different ways in which we can calculate bond order. So if you have a picture like these antibonding bonding scenarios, you're going to have to use this new bond order formula. So we've got 2 different ways in which we can calculate it. If you see this chart, they're wanting you to use this different version of bonding order. All right, here is my oxygen. So with oxygen, we had a total of 8 electrons. And if we are putting here as 2, 4, 6, 7, 8, 2, 4, 6, 7, 8, and we always put them lowest to highest. These cancel out. There's no sigma bonds on the first energy level. There are no sigma bonds on the second energy level. Where the bonding occurs is with the pi bonds, with the p's. And so I put 1, 2, 3, 4, 5, 6, 7, 8. I put 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, with this, we are going to have some canceling out. And so that's going to push out, those 2 are going to push out one of those bonds. And now that shows you I've got a double bond that's going to occur. Okay. So the bond order, I have 10 bonding electrons minus the 6 anti-bonding electrons. So count the number of blues and you get 10. Count the number of reds, you get 6. Divide it by 2. So that was 4 divided by 2, and that equals 2. Okay, so that's our bond order with this. If we then go to nitrogen, which we've done a couple of times, calculating the bond order, 10 minus 4, there are 10 blues, 1, 2, 3, 4, 5, 6, 7, 8, and there are 4 antibonds, none up here with the sigma or pi's in the 2 p's, and therefore we have 6 divided by 2, which is 3, is our bond order. Now, we could have calculated that, again, remembering the number of bonds divided by the number of ligands, and that also gives you the bond order. All right, so let me scroll back up and let's do one more showing you why we have fluorine. Fluorine as a single bond, and we know that because it's a halogen. But let's go ahead and just prove it to you. And again, I don't know why I didn't include the 1s's. So let me just draw those in here. So 1, 2, 3, 4. Those are the first 2 electrons that are in the first energy level. And if I place those on here, we notice that they cancel out. Element number 9 is what fluorine. It has 9 total electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 2, 3, 4, 5, 6, 7, 8, 9. All right, now let's put it in. 1, 2 here, 1, 2 here. No bonding occurring. We put in 1, 2, 3, 4. So we have a total, sorry, of We have a total of 5 and 5. That's a total of 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So now notice this is going to cancel out. This is going to cancel out. It leaves me with only one bonding pair. And that's the reason why I have a single bond. Really, really complex stuff. Let's talk about the bond order of it. How many bonding electrons do you see? So let's count those, and I will circle those in a different color. So I've got bonding pairs 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 10 minus the number of antibonding 1, 2, 3, 4, 5, 6, 7, 8, minus 8, that is 2, divided by 2, and it gets 1, which is the bond order. And if we think about the other way of doing it, the number of bonds is 1 divided by the number of ligands, which is 1. It gives you 1. Both ways to calculate the bond order are consistent. All right. Well, thank you very much for staying with me. This is an addendum to our already new topic. So thank you very much for listening in on this new stuff. And I know it was done while I was absent. Hopefully you'll have time to review this before we take the test. Thank you very much. Bye-bye. Happy Thanksgiving.